Hello AP Chemistry and welcome to 15.7, Le Chatelier's principle. Now, really important. Q versus K, right, is how we compare where a reaction is at any given instant versus where it's going to be, right? So Q is where it is, and we can predict whether we're going to make product or reactant as we head toward equilibrium, right? Le Chatelier's principle now is only for analyzing a system at equilibrium, okay? So if a system is already at equilibrium and we disturb it, then we would apply Le Chatelier's principle, okay? So it's like Q versus K, but at a different, we would use the analysis at a different time, okay? And this figure sort of goes over, right, whether we, if we change concentrations or if we change pressures or if we change temperature. Go over this figure and make sure you understand it. All right. Now, let's say that our disturbance is the amount of substance, okay? Remember that equilibrium is defined by my K value, which means that, okay, let's actually write it out. So I know that K in this case is going to be equal NH3 raised to the second over N2 over H2 raised to the third, okay? This is what K equals, and this equals a constant number as long as we're at the same temperature, right? Which means that if I perturb one of these, right, so for example, here we're at equilibrium, and I add H2, yes? I add H2, which means that if I increase the amount of this has to stay constant, right? So then this is just an application of math, right? If I increase this, and this has to stay constant, what else has to happen, right? Right. And if we look here, that's what this figure tells us, right? If we increase the amount of H2 suddenly, we're going to consume that H2. We're also going to consume N2, right? Because they go hand in hand, right? We're going to consume both of these, produce some more of this, until we reestablish equilibrium, where these numbers will be different, but raised to their respective coefficients, one on top of the other, is going to lead to that same constant value. Yes? Okay. Which means that if we think about this, right, and any reaction that's at equilibrium, right, if we add some of this, right, it's like pushing the reaction this way, right? If I add some of this, it's like pushing the reaction that way. And it can go, it doesn't just have to be adding, right? So for example, if I were to take this out of the equilibrium condition, right, so in a sealed vessel, if I were to start extracting the ammonia produced, right, that would actually push the reaction forward. It's like pulling the reaction forward. Yeah? Does that make sense? Okay. Here, this is one of the diagrams from your textbook for how that actually happens on an industrial process, right? How we actually actively sort of remove the ammonia, right? So that way we can sort of keep the reaction going in a forward direction, because turns out the reaction between nitrogen and hydrogen, not incredibly forward moving without some help. Right? And note that we do have catalysts here in addition to the tinkering of the pressures of everybody, right? And note this is what a lot of industrial chemistry is, right? We take a basic process, right? Laboratory, like bench chemists, sit there and refine that process and say, oh, well, if we do these conditions and if we do those conditions, we can get the ideal production of NH3, right? And then an industrial chemical engineer would take that whole thing and say, how do we engineer something on a large scale that's going to get that done, right? Which is really kind of fascinating, right? That there are so many realms of chemistry that you can work in, right? You know, stuff to think about in case you're, pondering what to do with your future. All right. Pressure changes, right? Same sort of thing. Wherein if we have a system at equilibrium and we disturb it, right, it's going to go back to that same K value, okay? Right? Anyway, so if we increase the volume, which means decrease the pressure, right? So both those mean the same thing, right? Then the reaction is going to shift. The reaction is going to shift to adjust for that, right? So bearing in mind that we have our pressures here, right? If we increase the volume, decrease the pressure, my reaction is going to shift to, right, fill that pressure back up, right? To get back to that equilibrium pressure, right? By going to the side that's going to have more moles of gas, right? So here, if we look, 2 moles of gas to 1 mole of gas, so we're going to increase the production of A so we can reestablish that equilibrium pressure, right? Likewise here, if we decrease the volume and increase the pressure, right, we're going to try to decrease the overall pressure, which means shift to the side. That's going to decrease the number of particles colliding with the walls of my vessel. Yeah? All right. Do note that there are other ways to change pressure, right? Your book mentions it briefly, right? That we could add an inert gas, right? So if we were to pump this full of neon, for example, that would increase the overall pressure, yes? But, ding, 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 right, it doesn't change the partial pressure of A or the partial pressure of B because neon is not a part of this equilibrium system, yeah? All right. Next up, temperature changes, right? Let's say we have reactant makes product plus heat, meaning this is what kind of process? Right, an exo process. If we were to have an endo process, it's like saying heat is a reactant. Now, do be mindful in your wording here, right? We should not say in an exothermic process, heat is a product. No, right? We would say that in an exothermic process, heat is like a product, and therefore the addition of heat pushes the reaction in the reverse direction such that we consume that heat and the other products to produce reactant. Now we would also have to discuss the fact that K is also changed, right? For an exo process, if we, and of course you're always just going to think about this, right? Where K is always going to be product over reactant at its essence, right? Here in this situation, if we increase the temperature and we shift in this direction, meaning we increase the amount of reactant, what inevitably happens to K? Right, at that new temperature, my K is going to be lower, yes? At that new temperature, my K is going to be lower in this scenario, right? For an endo process, if I increase the temperature, again, it's at equilibrium. If I increase the temperature and I add heat, heat is like a reactant, so the system will consume the heat and the reactant to produce more product, leading to an increased value of K. Yes? Increased value of K if we produce more product. And we could also analyze it from the other point of view, right? For an exothermic process, if we were to remove heat, meaning decrease the temperature, right? If we remove heat, since heat is like a product, the reaction will shift to produce more product, consuming the reactant, doing what? Right, increasing the value of K. Yes? All right, think through those, make sure they make sense, and make sure you can reason the same thing for an endo process. All right, finally, a catalyst. If we have a system at equilibrium, I'm not sure why we would add a catalyst once we've reached equilibrium, but anyway, again, going back to what a catalyst does, right? Catalyst lowers your activation energy, but it does not change this relationship, yes? All right. And going back to the graph that you guys doodled in the previous chapter, right? Again, if this is my uncatalyzed reaction, which is slower, right? Catalyzed just means we get to that place faster, right? Nothing about catalysis says that we change how much is present or change the identities of A and B. It just means we get there faster, yeah? Which is what this graph implies. All right. Thank you for listening. Be good, and I will see you soon. Bye.